Hi, my name is Sean McKeown, and I'm actually a lecturer at Napier now, but this is going to be presenting work for my PhD, so I kind of snuck in through the back door, sort of thing. I'm still technically a student as well, so this is actually fine. I'll have the contact details at the bottom the whole time, and then again at the end if you're really super interested in forensics. I'm actually glad the room is not completely empty, because forensics is sort of like the weird stepchild of the security world, and it sort of sits in the corner most of the time, so thanks for coming and supporting my choice and research area.
You're going to say great colour.
Sorry?
He's a forensics expert here. So.
Sweet, cool. Then please don't shout out when I'm wrong. I should say it, really. Right, so the title is Utilising Reduced File Representations to Facilitate Fast Contraband Detection. Bit of a mouthful, that's the title of the thesis. Hopefully it'll make more sense in a minute, at least. So the scenario we're talking about here is one that Kinga just touched on a little bit, and basically it's about detecting contraband images. Contraband just being another word for illegal, and in the public sector that means pretty much one thing, and I'll leave it there. So the public sector forensics, most of the work is pretty much to do with illegal images, illegal media, that sort of stuff, and most of the way that this is detected, at least at first, is using cryptographic signatures. So basically you've got your image of a random statue in Glasgow, you pass it through some hash function, in this case SHA-256, you get a fairly long cryptographic string that shouldn't match any other image but just that one, and you look it up in a database. And that's pretty much it. That's the first wave of detection. If we've seen it before and it's in the database, it should be flagged up by this. Now the problem with this approach is, amongst other things with modifications and stuff that I won't bother talking about, there's just so much data to look at, right? So digital forensics is suffering a massive backlog, and it's been a problem for the last 10 years or so. Well, actually maybe more like 15 now. Given that there's so many more devices per investigation, so if you think about kicking in someone's door, they've got a phone, they've got a laptop, they might have a PC, they've probably got a PS4, a smart TV, some kind of thing for receiving Hulu, Netflix, that sort of stuff. If anyone else lives there, they've probably got the same stuff again. So you might, kick in one house door and come out with 10 devices. And now you have to figure out what to do with that. And then that's compounded by the fact that the volume for each of these devices is increasing year on year. So back when I had a Windows 95 machine, probably around 1995, the hard drive is 2 gigabytes. That is laughable. That is like half of the RAM on my phone, right? It's nothing, absolutely nothing. So the forensics tools were really created for those size of drives. They don't really like the whole 4 terabyte stuff that's going on just now. So because of the volume, because of the number of devices, because of the tools just being really old and not really advancing the times as such, Britain, at least in 2015, had a backlog of 1.5 years. And the year after that, Ireland recorded 4 years. So seize a device, put it in a warehouse, we'll get to that in 4 years' time. Fantastic, right? That's not any use to anyone. And really, part of the problem, or a lot of the problem, as it turns out, is that there's this storage media bottleneck. So we've got a 4 terabyte drive, but it takes 8 hours to actually read everything off of it. So you can think about the data as this big reservoir, a big pool of water. But to get it out, we have to put a little tiny pinprick in the bottom of it and just wait for it to all seep out. So that data stream is really thin. That's the read speed. That's the 133 megabytes, which is actually pretty solid for a hard drive. And if you look back, I've got some nice numbers in my thesis. I don't remember them off the top of my head. But essentially, that sort of 2 gigabyte drive, you might have read in an hour or less. I've got some drives that you could have read in about 2 or 3 minutes, based on the fact that the capacity and the ratio of the capacity to the read speed were actually much more in balance. And unfortunately, this whole scenario is only getting worse. So Seagate at CES, they had booths showing their new Hammer and their Mac 2 technology. Essentially, Hammer in the left-hand GIF, or GIF, depending on which brand of Philistine you are, the left-hand side is all about applying heat when you're essentially rating the magnetic flux to the drive. So they found that if you actually apply heat, you get a better signal and it holds it better for the tiny areas we're looking at here. So basically they can cram more things together on the disk. And the numbers they're talking about, they've actually got drives that are 16 terabytes already. is basically this year they're looking to ship 20 terabyte drives, or maybe by next year, depending on how it pans out. But in the next 5 or 6 years, they're looking at 40 to 100 terabytes, which is absolutely staggering for a hard disk. Fortunately, they're sort of bringing along this idea called Mac2, where you can have 2 read heads per side of the platter. So we can effectively double the read speed, maybe. The problem with that is you double the read speed, but the capacity is increasing by 5 or 10 times. So if you take the same kind of numbers and you move them down, actually it takes nearly 2 days to read a disk at that point. 2 days. That's insane. Even if you say, okay, it's as fast as an SSD, it still takes nearly an entire day at 22 hours. So it's kind of bonkers and it's not going to get any better. So let's talk briefly about the volume, the existing techniques that are being used in research just now. So if we again go back to this idea of having a big data reservoir, well, we could actually process that at the same speed we're getting off the disk, right? So we're draining it out really slowly, but we're doing all the processing and we're copying it forensically all at the same time. We're still going to take 8 hours to get everything off the disk, but at least we're doing something with it in the meantime. I should also mention that these boxes here, they're just references to literature, so you don't have to read them, kind of ignore them if you don't really care. But they'll be popping up every now and then, so we're still limited by that 8-hour window. Well, another solution is to say, well, we don't need that massive reservoir. We don't need everything on it. A lot of it's probably going to be benign, not really worth looking at. So what if we just selectively pick the bits we want to look at? And a couple of the methods in the literature really look at parsing the file system and saying, okay, there's like a big directory there. It seems to have 100 images. Why don't we look at that? This one just seems to have Excel spreadsheets. We won't bother with that one. And we can sort of base it on the type of case we're looking at. So if it's embezzlement, actually the spreadsheets are probably relevant. If it's stuff the police are doing, then we're really focusing on media. We want images and video. So it's all about reducing the data set to the point we can actually manage. And that sort of continues with some stuff that has been done most recently by Phil Penrose at Napier. And essentially the idea is, well, we don't need to care about file systems, we just need a disk, and we just need to plug it in. And then we'll just select random blocks throughout the disk, and we'll hash those and compare them with the database. And in doing so, we don't have to read 1, 2, 3, 4, 100 terabytes. We can maybe get away with reading a couple hundred megabytes, couple gigabytes, something like that. And the benchmarks are looking pretty good, especially for SSDs. So under an hour in most cases for this kind of analysis. And the nice thing about it is statistical confidence. So because you're doing a sample, you can reason about the target data size and the samples and the number of samples and say, well, actually, this is 99.999% going to happen. If it's there, we'll probably find it with this reasonable certainty, which is very useful. Now, I don't do that, so I'll go talk about my stuff, which is still about data reduction, as you might have gathered from the title, or you might not have gathered very much from the title, if I'm honest, but it's all about reducing the amount of data. So a reduced representation, as I've called it, is pretty much just a way of saying some kind of representation of the image that we don't need the full data for. So if you can picture the full image on the right, well, maybe we just want to look at the thumbnails, as Kinga was just talking about. So that's centralized, it's lower resolution, it's a reduced version of the full image. Another way is to say, well, we don't actually need to read the whole image, let's just read a tiny snippet of it. That could be front or back or whatever you decide, but I've got file-specific approaches, where you're looking at JPEG, PNG features, and I've got file-agnostic approaches, where it's pretty much just, we'll base it on a big block of data. I don't care if it's PNG, zip, whatever, just get me this block of data, and I'll hash that instead. So I'll essentially be mostly talking about this partial file stuff, just because the thumbnail cache stuff isn't quite, well, it's not published for a start, so I don't want to say too much about it anyway, but also you've just heard a lot about thumbnails anyway, assuming most of the people in the room were in the previous talk. So I'll just quickly blast through the thumbnail-based triage stuff, and you'll know what thumbnails are, just a small version of the image, normally used for Explorer, Finder, or Gallery, depending on the application. Or the operating system, rather. So if we take it back to this idea of having a big data reservoir, well, we're not sampling, we're not reducing the whole thing, we're actually just looking in, oh no, what have I done? Right. We're looking in one very specific place. Just saying, go here, that should have thumbnails for images on the entire disk. It's actually only going to be a few hundred megabytes, maybe a gigabyte and a bit, depending on how full it is. But we can ignore the fact that there's terabytes of data on here, right? If it's been viewed recently, it's probably in the cache. It's probably a good place to go. And the really nice thing about this is it's been there since Windows Vista. So Windows Vista all the way through to Windows 10 doing the same thing. The work I did mostly looked at the 95 pixel and the 256 pixel thumbnails. So that's like the smallest one, and then the sort of medium large. It gets to a different size when you look at the super extra large ones in the previews, but that's the most common format for them. And rather than talk a bit more about the triage, I'm essentially just going to talk about some of the difficulties. So it's not just as simple as hashing it and saying, yep, we'll throw it out of the database and look it up later. There's actually some complications because of the way that Windows versions store this stuff. So it turns out, after having looked at Windows Vista 7 and 10, I skipped 8 because reasons. A lot of the time, the pixel data is just different. So on the right-hand side here, we've got a Windows 10 thumbnail and a Windows 7 thumbnail, and this is just an image diff. So all the stuff in pink is different. Like, it could be like by, of a 255 color pixel, it might be 254 instead, right? So it's not necessarily a big difference, it's just that that pixel's different. But it turns out quite a lot of the images have got most of the image being different between the two. And that's kind of concerning, but it just basically means that you can't hash the image and get the same thing. And there's another reason for that, in that sometimes they just store them differently. So sometimes the header's different, especially for the bitmaps. So the bitmaps change like 3 times, I think, just by having a different header, even if you don't look at the pixel data. One of them also uses compression, bitfields compression, which I think is Windows 10. And yeah, so there's all sorts of small differences, and for the slightly larger thumbnails that use JPEGs, they've actually got different quality settings as well. So you're never going to get the exact same thing between them, so hashing wouldn't work, because if you change 1 pixel, the hash changes. If you change 1 arbitrary bit inside the whole thing, the hash changes, so you can't build a single database. Another even weirder thing that only happens with Windows 7, as far as I'm aware at least, is that some of the thumbnails aren't even extracted from the full thing. So on the right-hand side, this is the full image, and then you can see Windows 10 is basically just looking at the full image and saying, yep, create a thumbnail from that, done, sorted. Windows 7 does this weird thing where it depends on the size of the thumbnail. So the 96, which way around was it? 256 pixel thumbnails? Okay, the 96 pixel thumbnails look like this, but if you go up to the slightly larger 256 pixel thumbnails, it actually takes it from this. And I mean, that it looks like that, but it actually takes it from that. So in JPEGs, you can have an embedded thumbnail. So if I take a picture with my camera or my phone, it usually embeds a little thumbnail in there that can get used for displaying stuff. So it's a secondary image within the main image. So you can actually pull that out. But a weird thing that can happen is if you edit the full-sized image, it might not change the thumbnail. And this actually backfired quite heavily on someone, I can't remember her name, it was like 2012. She had a photo shoot, it was topless, and decided to crop it, put it on a blog post or something, and for some bizarre reason someone was mucking about in the EXIF and found that, yeah, there's the original image, she was actually like topless or whatever, and it was a whole thing they used. So this can happen, and oddly, if it happens on Windows 7 and you're switching between the small, the medium, and the large thumbnail previews, you see different things, which is just stupid. So, yeah, another reason the hashes are just going to be different. But that isn't really the thing I want to talk about, and I'm blasting through lots of time talking about not the main thing. So, partial file signatures is really what I want to get at. Okay, what's a partial file signature? Well, it's basically just chopping off a bit of the file and saying, let's read that instead of the whole thing. So if we come back to that sort of data reservoir analogy, which I'm really fond of for some reason, it's essentially just like taking the start or end of a file. So depending on how many files, how big they are, you'll get a different distribution of your sample essentially from the disk. But there's only really 2 main criteria here. We want the signature to be pretty unique, or unique at some scale, because otherwise the database isn't going to work. And we want it to be faster than just reading the whole image, because otherwise there's actually no point. And nice thing about this as well is it's deterministic. So you want to read all the files and process all the files. It's not just randomly picking them. So it'll be the same result every time, which is quite nice. So the first approach, and I'm not really going to talk about this in too much detail because there's 2 separate papers on just this slide. the PNG stuff, if you read about 1% of the file, just using some header things and a tiny, tiny slither of the actual image data, you can actually do quite well. You can build a signature which is pretty much 99.8% unique for some scale. In JPEGs, if you read about 1 to 3% of the file, depending on the size of the file, using the optimized Huffman tables, you can actually generate pretty unique signatures again, and they're quite useful. So on the diagram on the right-hand side here, we've got a bunch of header data, so that's like your EXIF, your compression tables, and then the rest of the data down here. So traditional hash would say, give me all the data, put it through some function. All I was really caring about here was the start, and not even all of it, some of the stuff from the start, and saying, give me that, I'll process that somehow, I've got a new signature. The generic approach is pretty much to say, well, I don't care what file type it is. I can either look at the start of the file or the end of the file and just grab a bit of it and hash that. And it turns out the start isn't very good because you've got things like Huffman tables and quantization tables that are the same for every camera. Well, not every camera, but that model of camera. Every picture I take with my phone is going to have the same tables, and color profiles and stuff are reused, so the start isn't very good. But if you take it from the end, you're pretty much landing in the end of the compressed data stream. So that's just raw entropy, and if you take enough of it, you get a unique signature, unless the images are basically the same, in which case you want the signatures to match anyway. So how unique? As you can see on the left-hand side of this, reading from the start of the file doesn't quite get too unique. So the Flickr 1 million dataset is aptly named because it's about 1 million images. The GovDocs PNG stuff is 108,000 or so. Didn't quite get to unique there, but if you read the last 4 KB from the end of the file, you can actually get a unique signature for 1.1 million images. So we don't really need it to be any better than that. That'll do for most use cases. And I'll just ignore the bit at the bottom for now for the sake of time. Right, so how did this perform? So we know, based on what I've said, and you'll have to take my word for it unless you want to read the papers, that reading the end of the file, unique, or unique enough for the sake of looking at a single disk. If you're talking about billions of images, then we might have a different conversation, but you don't tend to find billions of images on a disk. Although if it's 100 terabytes, then you might manage. So the performance is similar for the JPEG and PNG stuff, but I'll just talk about the generic block-based stuff for the sake of getting through this. So before I actually give you some numbers, I'll talk about some of the impacts, or some of the things that impact performance. So the main thing really is the type of drive. So if you know anything about how these drives perform, you'll know that hard drives just like to read things sequentially. They don't like moving about because you physically have to spin a big platter, physically move a head to it. Bouncing about on a disk doesn't work very well. SSDs don't care so much. They do things in parallel. It's all flash-based. They can pretty much just say, give me that block of data, give me that block of data. So their random 4K small block, small chunk of data performance is actually pretty decent. So if you compare the two, you can get up to about 2 megabytes a second randomly bouncing about a hard disk. But for an SSD, you can get a couple hundred megabytes. So it's going to work much better for reading those tiny chunks. The other thing to bear in mind is the file size. So obviously, if I'm only reading a fixed size from the disk, the bigger the file, the smaller a proportion of the file that is. So 4K is like half of an 8K file, but it's bugger all of a 10 megabyte file, right? So it's about the ratio of these things. And essentially, if you're reading the entire file, the bigger the file is, the longer that takes, right? It just takes more time. Whereas reading a tiny block of it is always going to take the same amount of time. And essentially that comes down to bigger the file, the longer it takes to full hash, but subfile stuff doesn't actually care. It's going to be the same. But the bigger the file is, the bigger that gap is. So the files are really small, they're about the same performance-wise, but if the file is really big, then you get this massive gulf, which is really where I'm trying to cash in a little bit. Another thing to bear in mind is the file system might have some overheads. So basically you've got this kind of tree structure and you want to get to this, but you have to bounce through the subdirectories and the folders and get the path and read the file system's metadata. And that takes a bit of time. It's not free, especially if you're doing it like 1 million times. But it turns out in experiments, unless you're using the NTFS driver on Linux, which is a bit garbage, NTFS and ext4, so the Windows file system, the Linux file system, are basically about the same performance-wise. But if you're using stuff over a network, then NFS is actually much better at these kind of small accesses than Samba. And you can do some sort of magic with logical block addresses where you pre-process the entire file system, essentially, and you get all the blocks and you say, this is where we're going to read, and then you can optimize it so that this is less of an issue. Another thing to bear in mind as well is the number of threads. So you can do many simultaneous reads on an SSD, but it's going to negatively affect performance on a hard drive, because the hard drive just wants to spin through everything in one pass. An SSD can dart around and do things in parallel. Sorry, I'm going a bit fast because I spent too much time at the start. Right, so actual performance numbers. The main thing to focus on here is that we're comparing it to the baseline. The baseline being read the whole file and hash it. So if it's the same as the baseline, it's 1x, it takes the same time as fully hashing the file. If it's 10x, it means it's 10 times faster than that. Or in this nice diagram, it's like 10 drives rather than 1, really. The stuff on the left was done on Linux, which is why I've split up the NTFS and ext4-bit, even though I said they're fundamentally the same, because the NTFS driver on Linux is not great. And the stuff on the right is just to say that if you're doing it over the internet, it's about the same as a gigabit LAN connection. But essentially, doing it on hard disks, you can get about 3 times the performance of reading the whole file, which is pretty decent, even though I've just said it's not optimized for this kind of access. And obviously, the bigger the file, the bigger that number will be. On an SSD, you can get, well, depending on whether or not you're on Linux and depending on the file system, you can get anywhere between like 20 and 70 times performance increase. So I can do 70 times as many lookups in the same amount of time on an SSD, effectively. So if you're talking about, oh, that would take a day, well, this would take, well, I don't know, an hour or less, even with some overheads. And it actually works really well across the network as well. Because the less stuff you have to punt across the network, the less stuff you actually have to read. You can get rid of some of the bandwidth constraints. So on Samba, it was about 10 times faster. On NFS, it was a fair bit better than that, about 26 times faster. But really, the winner here is just doing subfile hashes on SSDs, because it just works really well. Anything else to say? Right. Yeah, so it still works on hard drives. The bigger the file, the bigger the difference is going to be. But these numbers I'm giving you are for actually reasonably small files. So if we go back to this graph I had up earlier, the data sets are actually, at least the median and the mean values, they were focused around here. So a couple hundred KB for each file, which isn't really that big. If I take, well, I don't know how big it is for my new phone, but I had an S6 before, and the average image size was about 5 megabytes. Which would place you off the end of the thing somewhere. So yeah, it would be about here, which is a massive difference. So I was being quite generous to the full hashing approach when I was putting these numbers together. I was taking file sizes that are maybe a bit smaller than I'd actually hoped to see. So that basically means these numbers get inflated massively. In fact, if you project this line forward and use a bit of machine learning, sort of linear regression, pretty much just draw a line through that and project it forward at 800 KB. It's about 30x, so 30 times faster than fully reading the file and hashing it, at least on an SSD. But if you go up to 10 megabytes, then it's actually more like 300 times faster or more. So dial that back a bit. 10 megabytes is maybe a bit too fast. Sorry, a bit too much for a picture. But you know, if you had a 5 megabyte image, the gap is going to be huge. So that's kind of the whole crux of my PhD, is saying, hey, look, these are completely different things and I'm awesome or something. Yeah, it's worked so far. We'll see how the Viva goes. So yeah, I maybe accelerated slightly too fast, but hopefully people got that. So the basic takeaway is that you don't have to read the entire file to generate a signature that you can use in a database. So I don't need that whole 5 megabytes of the file to generate something that's unique to that image. Actually, I can just look at the last 4K. This kind of thing is really good on SSDs, not so good on hard disks, but if your image data set is really high resolution, then actually it's still good enough. And you have to bear in mind things like, what is the total transaction cost? So how expensive is it to perform a lookup in the file system? How long does it take to seek on a hard disk to that thing? What is the ratio of that cost to the size of the file? If I'm doing it across the network, how much bandwidth do we have? What's the latency? So there's actually loads of different questions you can ask, but fundamentally it works awesome. And the really neat thing about this as well is just this bottom point here, is that There was some stuff on subfile forensics, but it was mostly breaking up the whole image and hashing all the blocks. So I'm basically saying you don't need most of those blocks. You can just use some of them to find the stuff. And there's not been a lot of work on basically exploiting the behavior or the performance characteristics of SSDs to speed up the forensics process. Because most of the time we're assuming there's a hard disk. But as you'll find with every mobile device that's been produced in the last, 10 years, it's all flash-based. All of your laptops are probably going to have an SSD. You're buying newish ones because hard disks are kind of going out of fashion unless you're Seagate. So hopefully that kind of made sense. I'm happy to take questions, and if you're super duper interested, that's the list of publications where all the materials come from, and hopefully this latter one will be published in the near future on the thumbnail stuff. Sorry, did you have a question? Yeah. No, the guy behind you. Yeah. No, the guy, please, sorry, please share.
Is the hash of a screenshot of an image different to the hash of the source image?
Yes, because the encoding will be different. The trick is you would basically need to reproduce the exact same encoding procedure. So if you had the same encoder and you knew everything about how it was compressed and stuff, you could probably generate it, but...
If you want to share dodgy stuff on Google, you can screenshot the source.
Yeah, or just save it in like a weird format, or do literally anything to change it in any way and the hashes won't work. But don't do that anyway, apart from the fact that it's super illegal. There's also this technology called PhotoDNA that's used in a lot of cloud providers, and they're not looking at the binary hash, they're looking at pixel stuff. So basically it would generate a hash from the pixel data, which would then...
I thought that's what you do as well.
No, I'm still looking at binary stuff. Although the thumbnail paper that I haven't published is looking at perceptual hashing, which is... I didn't mention it during that, I probably should have. Sorry, do you have a question?
So I think you've sort of partly answered it there, but this doesn't then stand up in like an adversarial like situation. If I just alter the image, then
well, this
you're talking about the image staying the same, right?
Yeah. Well, as long as you don't change the last 4K, actually, for this is fine. And the regular setup where you're hashing the whole file, any bit changed would knacker it. So that's always a problem. So if anything, this is better off than that, but still susceptible to the same kind of thing.
Is this faster than like fuzzy hashing as well?
That fuzzy hashing is way slower. Any of the bitewise stuff or the perceptual stuff, because it has to take into account similarity rather than just identity, it's much slower, especially the pixel level stuff. So this is just regular crypto hashing, which makes it really fast. Yeah.
Thank you.
Cheers.
So, I mean, this is effectively triage, isn't it? You would not do full forensics later, but
well, you can do both. So you could do clever triage if you combine the subset selection stuff that I talked about at the start. So parse the file system, look at some directories of interest, then do that. You're combining the two. But really what I was looking at was making it faster to process the entire drive and get it all out of the way, so that, yeah, you're not having to read the entire terabyte or the entire 100 terabytes ever, because that would take a long, long time. All right, have a good time for one more? Okay, sorry. On you go. I think we've got 2 minutes or so.
So you still have to generate a database of all these kilobit hashes for all the dodgy stuff before you can then apply it to...
Yeah, exactly. You'd have to go back and process, and because I'm actually doing it at a logical level rather than the block level, the disk block level, I don't think any existing database would even work at all. So, but that's always a problem.
Yeah,
not from new technique. Yeah, it's worth mentioning though. So, I probably should have included that somewhere. Is that the last question?
So when you're talking about the last 4K, are you talking about logically the last 4 kilobytes of the file, or the last 4K?
So I actually, because I thought I'd be talking about that, how do I make that?
Anticipating your questions, sir.
No! Right,
You'll need to unhide it first, I think.
Yeah.
Right click on it.
Unhide it, it's right. I was hoping that I could just maximize it based on Mac, so it makes it difficult. Why is F5? No. Right, okay. Ah, come on. Was it Shift F5 to get the current slide? Yeah. Right, you can see it, it's fine.
This is PowerPoint's fault, not the man. You leave that alone.
But yeah, essentially, it's not including slack space, it's not including the block boundaries, it's basically just saying, from the logical end of the file, read back 4K. So technically, you could actually be straddling across two sector boundaries. Sorry, one sector boundary for 2 sectors. But that actually provides it a bit of robustness, because it means if you append some random garbage at the start, you're not worried about how it aligns later on. So you're only looking at the actual content of the file rather than the accident of how it aligns. So I think we're good. Right, well, thanks a lot.